Okay, so um, in the next few lectures, we're going to prove the contraction mapping principle. So in this particular lecture here, we're going to consider step number one. So here we assume that xn is some sequence in x defined inductively by x sub 1 is equal to t of x sub 0, and x sub k plus 1 is equal to t of x sub k. So we want to show that the ordinary distance between x sub k plus 1 and x sub k is less than or equal to c to the power k times the ordinary distance between t of x sub 0 and x sub 0 for every possible integer k. Okay, so to prove this, we're going to use the principle of mathematical reduction. So if k is 1, that means basically we want to show that the ordinary distance between x sub 2 and x sub 1 is going to be less than or equal to c times the ordinary distance between t of x sub 0 and x sub 0. Now we know that from the inductive definition that basically x sub 2 is equal to t of x sub 1. So the ordinary distance between x sub 2 and x sub 1 is going to be equal to the ordinary distance between t of x sub 1 and t of x sub 0. But remember, because the mapping t is basically a contraction, so that means the ordinary distance between t of x sub 1 and t of x sub 0 is going to be less than or equal to c times the ordinary distance between x sub 1 and x sub 0. But remember, x sub 1 is equal to t of x sub 0, so that means c times the ordinary distance between x1 and x sub 0 is going to be equal to c times the ordinary distance between t of x sub 0 and x sub 0. So we have the ordinary distance between x sub 2 and x sub 1 is less than or equal to c times the ordinary distance between t of x sub 0 and x sub 0. Now, the second step in the proof is to assume that the inequality holds for k. That is, the ordinary distance between the ordinary distance between x sub k plus 1 and x sub k is less than or equal to c to the power k times the ordinary distance between t of x sub 0 and x sub 0. Then we want to show the inequality holds for k plus 1. That is, we want to show the ordinary distance between x of k plus 2 and x of k plus 1 is less than or equal to c to the power k plus 1 times the ordinary distance between t of x sub 0 and x sub 0. Now, to see that this is true, note that x sub k plus 2 is equal to t of x sub k plus 1, and x sub k plus 1 is equal to t of x sub k. So that means the ordinary distance between x sub k plus 2 and x sub k plus 1 is going to be equal to the ordinary distance between t of x sub k plus 1 and t of x sub k. But because it is a contraction, that means the ordinary distance between t of x sub k plus 1 and t of x sub k is going to be less than or equal to c times the ordinary distance between x sub k plus 1 and x sub k. But remember, by assumption, the ordinary distance between x sub k plus 1 and x sub k is less than or equal to c to the power k times the ordinary distance between t of x sub 0 and x sub 0. So that means c times the ordinary distance between x sub k plus 1 and x sub k is going to be equal to c times, into parentheses, c to the power k times the ordinary distance of t of x sub 0 and x sub 0. But then c times c to the power k is simply c to the power k plus 1. So c times the ordinary distance between x sub k plus 1 and x sub k is going to be equal to c to the power k plus 1 times the ordinary distance between t of x sub 0 and x sub 0. That simply means the ordinary distance between x sub k plus 2 and x sub k plus 1 is going to be less than or equal to c to the power k plus 1 times the ordinary distance between t of x sub 0 and x sub 0. So we've shown that the statement holds for k plus 1. So by the principle of mathematical induction, the statement holds for all k.